Go ahead and start the recording, then we'll start with that. Okay, so what is your question about that? Do you want me to go over the rules, or do you have a particular question you want me to work on? Okay. Now, is this a particular question in the homework or just in general? Okay. Give me just a moment. Let me see if I can log on to. You remember the question number? That way we can go over the exact one. Let me see. How do I get to the homework? That will be E, right? Chapter E. Okay. Let me see if this path will allow me to go to the homework. Okay, chapter E. I know you guys have a very different view than I do. Let me use the student view so that you can, with this one here. Okay, so I can kind of hear whenever you write something. So if you know what question that you're talking about, we can go over that. And then, okay, let me pull this up. As you can see, I changed, I guess there was an issue with the setting for the first couple of questions. So you should be able to work on the homework even after the due date has passed. Okay, so hopefully you can see my screen right here, right? So I'm assuming not this one here, not the one with the graduated cylinder, right? So let me know when I get to that question. So not this. My computer is slow. Because you said multiplication and division. Let me see if I can find that. That's adding and subtracting. This one here? Okay. So what I'll do here is, oh, that's interesting. Okay. Let me put this on the right, and then I will just go through a couple of these. Oh, move screen. I think my computer is just tired of working. So I'm going to add a couple of pages to my iPad so I can write on this, because the only surface I can write on right now is my iPad. Okay, for those of you joining me, we're working on a couple of questions in the homework before I start with a new section. If you do have a question on the homework, send me an email and say, can you cover this in class? So it makes it easier then for me to kind of be prepared. But we're doing that right now. So let me see. I'm adding a page here. So we are working on this. So this question is not just about multiplication and addition. You also have the PIMDOS, right? So we have to go with 333. Oh, hold on. Sorry, I got distracted by that text. Times 2.98 plus 376.70. Let me minimize that so I can actually have the room. Okay, we're dealing with a question that requires PIMDOS because you have so many different orders of operation here, right? So many different operations. So what I'm going to do right here, let me move this over. I can still write on the side. We need to start with parentheses first because it's PIMDOS. Parentheses first. Then we'll do, in the order, exponents, multiply, divide, add, subtract. So I'll do this stuff in parentheses first. Now, the way they do it in the book is you don't round off first, you just keep track of it, okay? So what I'm going to do here is 20 point, I'm going to count significant figures. I got 1, 2, 3, 4, 5, 6. This number here is 6 significant figures. This number here is 3. 1, 2, 3. I got 3 significant figures. Okay? If the process of tracking significant figures that I showed last time was too complex for you, what you can do just to be safe is keep your answer one more significant figure than what you need. So what I mean by that is, let me start with a number in the parentheses here, okay? I'll multiply these out. Now I know my answer has to be in 3 significant figures, right? Because the least number of significant figures controls your answer. So I'll start with the first one, 20.9333 times 2.98. And I get my answer, in parentheses, as 62.381234. So I'm writing the full number, right? And then plus 376.70. Now this has to be rounded, approximate this down to 3 significant figures. Okay? It has to be rounded down. That means this number makes it, that number makes it, and then of course that number makes it. And when I'm saying the number, I mean the position, right? This number remains as is, as is. Now this is where I cut the number off, right here. So since I'm going to be cutting the number off right here, the number to the right of the cutoff point is greater than 5. Well, it's greater than 4. If it's bigger than 4 or 5 or above, then I have to add, you have to add a 1 to the 3. So plus 1 to the 3. So here, I'm going to go down to 6, remains as is, 2 points. Now the 3 has to become 4. Oops, this is supposed to be 4. And then I can move on from here. This is now 3 significant figures. So I'll make this simple like that. And then I'm going to add 376.70. Okay? Right there. Okay, now that we're done with the multiply rule, now we have to use the add rule. Remember the add rule, you have to line them up vertically and make sure your decimal places are stacked. So you take this, you take the 6, 2.4, and then line the number below it. Make sure the decimals are lined up like that. 376. Right? So to make it easier, even though this used to be 3 significant figures, right? Remember it was 3 significant figures? And this one here, just counting significant figures, is 1, 2, 3, 4, 5. This is 5 significant figures, right? This is true. But in the adding and subtracting, we really don't care about this to get our answer. What we care about is decimal places. And so in the top number, I have 1 decimal place, 1 number after the decimal. In the bottom number, I have 2 decimal places, 2 numbers after the decimal. That means your answer, once you add these 2, should have 1 decimal place. The least of the 2 controls your answer. Okay? So once we get the answer in 1 decimal place, that will also be the correct significant figure. So I'm going to add these 2. That's what they said to add, right? So I still have my old answer in my calculator. I think it's easier, even though I'm writing it like this, I keep my old answer in the calculator, the one that I had up here. I think it makes your life a lot easier. Then add 376.70. Add 376.70. When you add that, I get, let's see, 439.08. I can leave the rest of the numbers here because remember, I only need 1 decimal place. That means that this position here will make it. Well, starting from the left, this makes it, that makes it, the decimal makes it, that 1 decimal place makes it, the 8 is the second decimal place, it doesn't make it. So what I'm going to do here is, as usual, I have to cut it off right here. Only the 0 position makes it, right? Once again, I look to the right of the cutoff point. To the right of the cutoff point, that number is 5 or above. So I have to round up and add a 1 here. So this becomes 439.1. So this is the same thing as 1 decimal place, right? Because it's only one number after the decimal, to the right of the decimal. But when it's significant figures, I actually have 4 significant figures. Okay? So hopefully that helps, right? You want to make sure you follow the PIMDOS rule first if you have many different operations, and then you round up as you go. So I try to keep it simpler this time. And like I mentioned, right, you can go ahead and round this off early. Actually, when I was in school, I never did the complex stuff that they're doing in this school, I mean, in this book. I just rounded off early and I went along. But what I did was I left my answer in my calculator, so I wasn't pressing clear. I was leaving the previous answer I had and then continuing with the operations and then rounding up as I went. Okay, so let me try to put in my answer here to see. It better be right. 439.1. Oh yeah, so you see how they leave the whole number, like all these places. So as I'm saying, you can round this up if it feels a lot easier for you than to keep track of things, but leave this number as is in your calculator. So when you're adding here, it works out, right? So you see, I got my answer just like that. Okay, do you want me to work on another one? I'm trying to see which. Ooh, you know what? Let me work on D. D looks exciting, right? Because D has got parentheses, but it also has scientific notation. That should be fun. So I'll work on that. Oh, let me add more space right here. Okay, so right now, let's see. I'm working on D. Let me make sure this is recording. Yeah, I'm working on D. And so I will write here 2.72 times 10 power 6, close parentheses, divided by 46.763. You have brackets here. So the parentheses and the brackets are all just saying do this first, right? And then you add 139.24. So we're going to add last. Okay, so parentheses. We'll start, since this is divide, you start by assigning significant figures. So in this format of the number, scientific notation, only this part here is assigned. So this will be 3 significant figures, right? All 3 numbers are significant. Over here in this number right here, 1, 2, 3, 4, 5, I have 5 significant figures. So in the end, the 3 significant figures is what your answer should be rounded up or down to. Okay? So with this one here, like they actually show, you want to place your scientific notation in calculator, in the calculator in parentheses. It makes it easier for your calculator to understand what you're trying to write. So I'm going to write here, open parentheses, 2.72, and then I have the times 10 power n. So I'm going to write 2.72. The button I have is times 10 power n and then 6. And that will actually write this number for me. So open parentheses, 2.76 times 10 power n. I'm pressing that button and I'm writing 6. I have to write right arrow, then close parentheses. And that helps me write scientific notation. Then I'm going to divide this by 46.763. Okay, then divide by 46.763. When I do this, what do I get? I actually get, oh, a huge number. 1271953. You can see my calculator is known scientific notation, right? 127195360. Okay, Since only 3 significant figures can remain, now you start counting, right? Don't forget this part here, 139.24 plus 139.24. Now, I don't clear my calculator. I leave that number as is, this long number in my calculator, leave as is. But out here, I round it up, right? I have to round this up or down to 3 significant figures. That's what I said right here. So this number remains, this number remains, this number remains. The cutoff point is right here. But don't, since the number is really large, all you do here is convert these other numbers to 0, okay? So looking over here, I got 1, 2, and 7. The next number is 1. It's less than 5. So that means all the numbers after that become 0. You don't want to make this just 1, 2, 7, and then that's it, because it will make the number very small and it doesn't maintain the integrity of the original number. So what you want to do here is write 127. That's correct. And then where 1 is, you put 0. Where 9 is, 0. Here, 0, 0, 0, 0. So the remaining numbers all become 0. And this is how you have 3 significant figures. Okay? So 127, 0, 0, 0, 0, 0, 0. Yeah, I have to have, 6 zeros after 7. I had to count to make sure. So now this is 3 significant figures, and then now I add this to that, plus 139.24. Okay, now you have to line up your decimals, right? So when I'm lining up my decimals, 127, 0, 0, 0, 0, 0, 0. This number has no decimal, right? It has no decimal the way I have it right now. So I'm going to add this number to the bottom number, which has a decimal. So this is going to be like this, 0.24. Then I have 139. So I'm going to add these two. Yeah, this is a complex question, but you see how it goes, right? I'm going to add these two. Let me make sure. Oh, you know what? Sorry. I just realized something. I wrote divide here, but when I was doing my operation, I just looked at my calculator. I think I did multiply, right? Anybody notice that? I think I did multiply. So let me make sure I got the right number, because I was looking at it trying to figure out why they gave us this weird question. Let me work that real quick. Exponent 6 to the right, close parenthesis. Supposed to be divide 46.763. Yeah, all that ding ding sound I'm hearing from my computer is actually distracting me. Okay, that's a lot better. Sorry about that. I pressed the wrong operation, and that's what I was trying to figure out why my number was so off. Yeah, so I'm supposed to divide. So once I divide that, I get 58165.64378. That makes more sense. Because the other number seemed a little bit very complex. That's why I was wondering if I'd done something wrong. Yeah, you have to divide that. Once you divide that, let me see. Once again, it has to be 3 sig figs, right? So this number makes it, this number makes it, this number makes it. The cutoff point is right here. So now I have 582, right? Because you have to round the 6 by adding 1 to the 1. And then I end up with 0 here and 0, right? And then you add 139.24. Okay, so now I'm going to try this. It's still that weird point, but I think this is a lot better. I arrange this in the vertical fashion because you're adding 58200. There's no decimal here, so leave it as is. The decimal goes down here, 24139. Now we're going to add. So when I add these two plus 139.24, let's see what we have. I end up with 58304.878. Okay, this one here has 0 decimal places. This one here has 2 decimal places. So your answer has to have 0 decimal places because that's the least of the 2. That means all of this must drop off. This number makes it, this number makes it, this number makes it, this number makes it, this number makes it. Everything after the decimal to the right of the decimal does not make it. Okay? So since this number, my cutoff point is right here. Since this number is larger than 4, or is 5 or larger, you want to add 1 right here. So I have 58305. Okay? Let me try that number and see how that works. Now you can write the number as is. You can write it scientifically. Let me write the number as is and see if that works. 58305. It might say something about the way I rounded up. Oh no. Okay, let me double check my work and make sure, because 2.6 exponent 6. Man. 2.72. I thought I did this correctly. $46.763, and then I'm adding 139.24. Yeah, I'm thinking they want me to put this in scientific notation. So what I'm going to do here, I'll write this in scientific notation and see if that works a lot better. I'll write it as 5.8305 times 10 power, let's see, 1, 2, 3, 4. I'll write it in scientific notation. Does it allow you to change it right here? 0.8305. Okay. And then let's see, how do I put this over here? Let me put a 4 here. Man. Yeah, this is really. Okay. So you know what? Let me do this. Instead of working this over and over again, was anybody able to work this one here? This one out? Instead of working this over and over again, let me see if I can do a request, because I didn't realize how complex this question was when I assigned it to you guys. I thought it was just simply straightforward, because you should do this one here first and then divide it by that as it shows in parentheses, and then just add it to that. That's a simple operation here. I'm trying to figure out why it's just not working it out. Was anybody able to figure this part out? I mean, I've done the operation 3 times, unless I'm not doing it. Is this not set up properly? Okay, let me try one more real quick here. Unless they want me to continue this whole process with scientific notation. Let me see what you said right here. So let me do this. Yeah, that question is a complex question, just in case you're wondering. None of the exam questions will be that complex, okay? They're usually more simpler than that. I think what the issue here is I have to continue the whole operation in scientific notation, because if you don't do it that way, then it kind of, they're not really accepting the answer the way I wrote. I don't think it's necessarily an issue of the answer being, the magnitude being correct and not correct. The issue here is about the format I'm writing it in. They're not accepting that format. So let me do this. I'll keep the scientific notation so that this format here rules the way we are writing everything, then that will influence the answer, okay? So what I'm going to do in future is just get this kind of question out, because it's having you work this, and the way they're working things out in this book, we're not going to be working it out in many other places. So let me do this last one here, keep it in the right format, and then we'll move on. We'll start with the actual lesson for today. Okay, 2.72 exponent 6. I'll keep my answer in scientific notation this last time. I do apologize about that, because I didn't realize that they're going to have you do all this. Then divide once again 46, 2.72 exponent 6, 46.763. If you run into questions like this, just let me know, because I can try to figure out if the question is a of what I'm trying to assess with you guys. So this second time around, I'm going to keep my answer in the right format and write it as scientific notation. So you probably wouldn't have known about that just by working the problem out. Okay, so I have to write in this form, and that will be 3, 4, like that, and then plus 139.24. So that might actually work out right. I mean, that might be the answer. So I'll try to keep it in this format and then add 139.24. I mean, ultimately, it ends up in the same way. The only difference this time is the decimal places, right? I still get the same setup. Times 10 power 1, 2, 3, 4. Okay, let me try this and see if this works a lot better. 5.83 exponent 4. If I can't get this to work, I'll just remove the question because, oh, no, I didn't even finish this question. Oh, let's see. Okay, let me write this down. I'm going to remove this question because I cannot figure out exactly what format this is supposed to be in. Hold on, let me try one more time. I think I put the 4 in the wrong place. Okay, so that was the issue. Like y'all see, the issue was I had to write the number in scientific format to get the right answer. Okay, once again, I didn't realize this question was that bad to where the way you write the answer, because I mean, I got this answer a long time ago, but the way you write the answer does matter, right? So the issue here was everything had to be in the scientific format. Once again, since we have this right here, it's easier for me to leave the question in. For future classes, I'll just go ahead and delete that question because it's just unnecessary. Is there any other questions that you guys had issues with in the homework? Yeah. The issue here was if they start with a scientific notation, you have to kind of keep that format. Even though here you take it back to a regular number, you want to keep that format because that was the only way I could make the answer work to the way they want it to be. Okay, so other than that, let me go ahead once again. So to summarize what I just did here, when you have multiply and divide, yeah, sometimes it even takes me a couple of tries to figure out exactly what the computer is wanting because it's a different way it was programmed in the computer, right? If you have multiply and divide, answer must be least significant figures. Okay? That's the rule. And this is the rule I was applying. If you have add and subtract, then the answer must be least decimal place. Okay? And if you have PIMDOS, like the question we had, then the way the questions are programmed in the computer, if you do have this at some point, as you saw how I had to try so many different formats to get the answer to match what they had, you want to make sure if you want to get the question right. If you can't, just ask me and I'll work it so many different ways to figure it out. But yeah, essentially, if you do have the scientific format, then you want to let that rule the way you answer your questions, right? And then, yeah, the scientific notation and that will give you the answer that you're looking for. Okay, let's go ahead and continue with this part here. Last week, we ended by talking about the mass ratio, right? And I mentioned this last week. The mass ratio is used to identify compounds. Used to identify compounds. Okay, that was last week. Now, in this law called the law of multiple proportions, this is actually using the mass ratio to figure out the way two elements can combine to form different compounds. Okay, so in that context, in that frame of mind, we're told John Dalton actually came up with this law of multiple proportion. So after figuring out the Dalton's law, he came up with an additional law, which is this law right here, the Dalton's postulates. It says when two elements, call them A and B. I usually don't like using generic elements like that because I feel like we can't really relate to A and B because they're not real elements. So how about we say carbon and oxygen, okay? And then let me give actual compounds. Carbon and oxygen can combine to form many compounds. I'm going to pick two common ones that we know about. Carbon and oxygen as in carbon monoxide, carbon and oxygen as in carbon dioxide. So you can see from these two compounds I have on the right, both of them have the ingredients of the elements, carbon and oxygen, right? So you have two elements, carbon and oxygen, that form two different compounds. The masses of elements B, so B will be oxygen, right? That combined with 1 gram of element A, carbon, can be expressed as a ratio of small whole numbers. What does that mean exactly? What they're trying to say is if carbon and oxygen can combine to form two or more compounds, there is a relationship in how they combine. They don't just combine randomly. There's a very specific way to combine so that if you look at the amount of oxygen versus carbon, okay, you look at the mass. So it says here masses. In other words, there are different masses of element B. So different masses of element B combined with just 1 gram of element A, which is carbon. In other words, different masses of oxygen combined with 1 mass of carbon. And when you relate these two, you get a whole number. Didn't we just learn this last week? And we call that number a mass ratio when we had a mass of oxygen compared to the mass of carbon. And then let's go back to this table right here and see. When we were done with this, right, we took 21.6, this was grams of oxygen divided by a mass of carbon, 8.10 grams. We essentially got 2.67, which is the same thing as 2.67 over 1, right? So this is like saying 2.67 grams of oxygen over 1 gram of carbon. So having this relationship here, they're saying, once again, paraphrase, the mass ratio of the top compound divided by the mass ratio of the bottom compound will give you a whole number. That's what they're trying to say. Equal whole number. Because the mass ratio is essentially the mass of the heavier compound, the heavier element over the mass of the light element, right? Mass of heavier over the mass of light element. So once you get those mass ratios and divide them with each other, you get a whole number. So let's see how that works with carbon dioxide. We're going to be comparing carbon dioxide with carbon monoxide. So even though in this question here, they're actually giving you masses, what I'm going to do is I'm going to use the atomic mass from the periodic table to find our own mass ratios. So we're going to prove, that's our goal, law of multiple proportions. That is our goal and what we're doing right now. So we're proving that law that does actually exist between CO2 versus CO. So let's start. In the periodic table, the carbon is essentially 12 grams per mole. The oxygen is 16 grams per mole, right? In this first formula here, I'm seeing of the two, oxygen is heavier. But in this formula here, we have twice the oxygen. So I'm going to say here, the oxygen mass is essentially 16 times 2, which is, I'm going to do this on the calculator because it makes me feel a lot better, 32 grams per mole. Okay? And we're dividing this by carbon mass because this is what we call the mass ratio. Okay? The mass of the heavier element over the mass of the lighter element. So now I have 12 grams per mole. Let me see what I get here for the mass ratio in CO2. 32 divided by 12. What do I get? I get 2.6, and the 6 continues for a very long time, so I'll just round it off here, 2.67. So 2.67 over 1, or just 2.67. Okay, that's what I was saying earlier. Whatever mass you have of oxygen over 1 gram, they were talking about this. So this is essentially the mass ratio, because remember, ratio is a number divided by a number. This is it right here. Okay, let's find the mass ratio for CO. Mass ratio. Again, take the oxygen mass over carbon mass, and then let's see. This time in CO, we only have 1 oxygen, so that will be 6 grams per mole. 16 grams per mole over 12 grams per mole. This is carbon, right? 16 divided by 12, we got 1.33, and the 3 goes on forever. I'll use only those 2 grams of oxygen for 1 gram of carbon. Okay, or you can write this as 1.33. Oops, I pressed the up button. There, okay? So the rule says here, you take the 2 mass ratios, divide them by each other, and you should get a whole number. We're going to prove this. If we divide these two and we get a whole number, the rule works. So we're dividing these 2 numbers, 2.67 divided by 1.33. 2.67 divided by 1.33. Well, yeah, if you use the numbers they gave you with all the repeating numbers, you do get 2, okay? Now we're doing all this. I remember when I was learning this in school, I was like, duh, that was so obvious. If you look at CO2 and you look at CO, you can just tell from the formula here that the top one, this one takes twice the mass of oxygen to make CO2. Why did we have to go through all of this just to prove it? What they're trying to show is that there is a relationship in the mass, the amount of oxygen used to make the first compound versus the second compound. That is essentially the law of multiple proportions, right? It's so obvious in this question here, but it's not always obvious in all questions. So I'm going to skip over this slide right here and go into this scenario. This is a scenario where the relationship between the masses of the second element, the heavier element, is not so obvious, okay? Now there's a lot of words here, but we're just going to read through and then get the information we need. We're told nitrogen forms several compounds with oxygen. So the 2 elements we're examining here and trying to figure out if they're able to form compounds that have the law of multiple proportion relationship, right? Do they have that whole number relationship they're talking about in this law? Do we see it here? The compound is formed between nitrogen and oxygen. That's what it says here. Including nitrogen dioxide. Now, we haven't done naming yet. So one formula that's formed when these 2 combine is nitrogen dioxide. The other compound that's formed, or the other formula, dinitrogen monoxide. So 2 nitrogens, 1 oxygen. So these 2 can combine to form either that or that. Okay. Measurements of the masses of nitrogen and oxygen that form upon decomposing these compounds show that nitrogen dioxide contains 2.28 grams of oxygen. So the oxygen is 2.28 grams of oxygen to every 1 gram of nitrogen. To every 1 gram of nitrogen. Okay, the heavier mass, the lighter mass. Okay. While dinitrogen monoxide, the second one, contains for oxygen 0.570 grams of oxygen for every 1 gram of nitrogen. Okay, so I'm right here. Show that these results are consistent with the law of multiple proportion. Show that when you divide these 2, they're consistent. So what I'm going to do here is, once again, this is the formula. You want to take the mass of the heavier of the 2 elements, which is going to be oxygen, over mass of nitrogen. Remember, this is essentially the mass ratio. So mass of oxygen, 2.28. They gave it to us in the mass ratio form, so it's so much easier. Oxygen divided by 1, I can say 0.00 grams of nitrogen, okay? And I get 2.28. Over here, for N20, once again, the mass ratio is mass of oxygen, the heavier one over mass of nitrogen. And this one here is what? 0.570 grams of oxygen over 1.00 grams of nitrogen. So when you divide that, once again, this being the mass ratio, we get 0.570. Now that we have the mass ratio, take the bigger mass ratio. So I'll say here, larger mass ratio divided by smaller mass ratio. This should give you a whole number, right? So the larger one is 2.28, the smaller one is 0.570. So if we get a whole number, the law is proved. If we don't get a whole number, it didn't prove the law, right? Just the combinations that were formed did not prove the law. Doesn't mean the law is wrong. 0.570. So we get, oh, look, we get a whole number. So we can say law is proved in these compounds. Okay, because the large mass ratio divided by the small mass ratio gives you that number. Okay, so I'm going to continue. We're doing good. Let me see. Yeah, I have to keep remembering to look at the time. I have a clock right here I'm looking at. Okay, so remember, just to quickly recap, we just went over last week Dalton's atomic theory, right? So what I'm going to do here is, if you were asked to sketch a picture of the atom that was described by Dalton, this is the sketch of atom according to Dalton. It would just be a round atom with nothing inside, because he essentially said all atoms are round. Then he said a lot of other things in his postulate, but he said there was nothing inside the atom. So he said there is nothing inside the atom. And so I'm paraphrasing what he said. So when he said the atom is indivisible, cannot be divided, this is what he meant, right? There's nothing inside the atom. The atom is indivisible. Remember, the successes of his theory were the three things we talked about. The law of multiple proportion. So I'm going to once again summarize it from last week. So this is kind of like the conflict management, right? We are about to tell him what he did wrong. But before we tell him what he did wrong, we're telling him what he did right. So his successes are, number one, the development of the law of conservation of mass. Scientists could never have, I shouldn't say could never, never is a strong word. It had taken scientists longer to come up with this law of conservation of mass, but once they read the theories from Dalton, they did more studies and figured out, hey, this works in chemical reactions. Mass is conserved. Second one, we saw the law of definite proportions, saying that when elements are reacting to form compounds, they don't just come together haphazardly and then you just form a compound. There is actually a definite ratio, right? Definite proportions by mass. We definitely have a ratio of the elements by mass that makes a specific compound. That's where we had the idea of a mass ratio, which says specific amounts, and the context here is mass, of each element combines to form compounds. That's the idea of the mass ratio. Then today we saw, of course, the law of multiple proportions. Okay, so now we're caught up. Now we're going to criticize his theory right here. As time went by, life happened, and then scientists came up with a new method of analyzing samples that were being discovered. Scientists noticed that if they took elements or compounds or whatever and they were able to vaporize them, so they took whatever sample they were analyzing, they were studying, they vaporized it, put it inside this cathode chamber right here. So this is a vaporized format or vaporized form of any element of the element. Now, the identity of the element did not matter. What was more important was that the element was in a gaseous form. It has to be a vapor. So they've evacuated the chamber, the cathode ray tube, that's the name of this device. They placed the gas version of the element. Right here you can see the cathode ray tube is attached to a high voltage device. One side of the cathode ray tube is called the cathode, that tends to be negatively charged. The other side is the anode, positively charged. And essentially, electricity is passed through the sample. What they notice is when attached to the high voltage source, a beam of particles was released. Okay? And these particles had a very unique characteristics. First of all, I'll say here, these particles travel fast. Okay? In straight lines. And then number two, were drawn to positive end. Okay? So you have the particles being released. A lot of them are being released. No matter what the sample was, same thing happened. Different sample. Helium, same thing happened. Nitrogen, same thing happened. Whatever it was, you had those same. So they call those the cathode rays because it was released in the cathode ray tube. Okay? And you can see here the particles were coming out from the cathode end. So they were sorry, they're trying to figure out what these particles were. So we're told here, a beam of particles traveled from the negatively charged electrode and they were drawn towards the positively charged ones. They were traveling in straight lines. The particles always form regardless of the type of element placed here. What does that mean? If they're always leaving the negative and they're leaving fast and they're being drawn to the positive, we know in science that opposites attract. Oh, I can't spell this morning. Attract. So if they're leaving the negative and they're drawn to the positive, they must be negatively charged. Okay? Because like charges repel and then opposite charges attract. So here, based on all they saw, their observations, they concluded these particles, whatever they are, we have no idea what they are yet. We will call them cathode rays. These are actually negatively charged. This one here they knew for sure. Okay? And they decided whatever was negatively charged is coming from inside the atom. There's something inside the atom that's producing negative charges. Okay? As time went by, more experiments were done, and then now the next scientist that you have to remember, J.J. Thomson. Okay, so here we're discovering there's some particles that are negative. We have no idea what they are. We can't make a conclusion they're electrons. We're not there yet. Now comes the scientist J.J. Thomson. He was able to measure the charge to mass ratio of the cathode ray particles, we still don't really know their real name, by deflecting them using an electrical and magnetic field. So they want to confirm. In science, when you produce something, somebody else has to confirm your observations. So all this was done just to prove the charge. And so J.J. Thomson is credited with the discovery of the electron. As I'm reading this, I'm actually reading this very differently, right? Because over the weekend I was binging. Yes, I was binging. Your teacher watches TV too. Well, it wasn't really TV, but it was I think HBO Max or something. Anyway, I was watching Big Bang Theory and I was watching the end of the season. And towards the end of the season, Sheldon and his wife Amy are able to come up with a discovery. I won't discuss that because it doesn't have anything to do with the lesson per se, but just the idea that since they did the preliminary work, somebody else did the work to prove their work. There was an argument that the person that proves your work can actually be the one that gets credit for it. Can you imagine that? The electron was first discovered by these scientists right here, right? But later on, and it wasn't just JJ, it was more than just JJ right here. But later on, JJ does extra work, and then he's the one who gets the credit for it. So it was very interesting to me, right? He carries on. They mentioned just his name, but he carries on, does the work, and gets credit for the discovery of the electron. Very interesting. And then you have Millikan's oil drop experiment. And right here, Millikan gets credit for discovering the actual value of the charge on the electron. So over here, they realize the electron is negative. And for the most part, we say the electron is -1. But in reality, this is not the actual charge of the electron. It's just the relative charge of the electron. And so I'll show you the table later on that shows you the relative versus the actual. So he does the actual work of figuring out the real charge on the electrons. I'm going to keep this part here very simple. In the work that he does, he figures out the actual charge of the electron, not the relative one, is -1.60 times 10 power -1 coulomb. Here's the thing. We rarely ever use this charge. There are specific calculations where you use the actual charge of the electron versus the relative charge of the electron. So for you guys as class, most of the time we're going to be using the relative charge. And remember, the relative charge is -1. Okay? So I'm going to move over and show you the table on the bottom. Where is that table? Give me just a moment. Let me get the table right here. The table on the bottom here shows you the 3 subatomic particles. So this is the subatomic particles. We'll go in order and learn each one that were discovered inside the atom. And then you see the actual charges, right? Right here. The proton has a similar charge to the electron, only it's positive. The electron has this charge right here. These are the actual charges, but we tend to use the relative ones because they are easier for us to relate to. Unless you're doing higher order calculations, these charges here are sufficient. The neutron will be neutral, the electron will be -1, the proton will be +1. Okay, this is what I'm referring to. So we'll get to that down the road. So let me move over. Y'all can read over the theories real quick about the discovery. So Millikan, once again, he is credited with figuring out the actual charge of electron. Okay, so moving on after that, once JJ has discovered that the electrons do exist inside the atom, he's done first experiment with a lot of people, second experiment to confirm the first experiment. Now he came up with his improved model. So when I think about this, I always think about, you know how you have your old phone and your old phone could do so many things, maybe a flip phone, and now it's the touchscreen phone and it can do a lot of different things. We have the old model, Dalton's atomic model, and then now we have the newer model right here. So let me draw the older one on the left, then we have the newer one on the right, okay? So the idea here is Dalton said you have the atom and it's round and there's nothing inside of it. Well, in the newer model, we are realizing, we agree the atom is round, but we are realizing there's more to it. Wait, yeah. There's more to it. Inside the atoms, you have electrons. And these electrons here, remember, these are negatively charged. Now, J.J. Thomson, I like to call him J.J. like I know him, J.J. Thomson. J.J. Thomson actually discovered the whole atom is neutral. If the whole atom is neutral, there has to be something positive in the atom, making sure the whole atom is neutral. So he said the core, all the purple, whatever color this is, purple, pink color we're seeing here, all of this is positively charged, but then you have the electrons in there. So this reminds me of like blueberries inside a scone or something, where the blueberries themselves are negative and then the whole interior of the scone is positive. Okay, so that being the case, the atom is still neutral. Atom is neutral because the positive counteracts the negative. And this is J.J. Thomson's model, and it's called the plum pudding model. Okay, it's a model where you have electrons spread inside the atom, but the core of the atom, all of the interior or the inside is positive. Okay, so we move on, and then we have Rutherford. I like to call him Rutherford. That's how we call him at home. Rutherford is actually a student of Thomson. So these people are kind of related sometimes, you know. It's his student. And he worked under him. And so Rutherford was so impressed by this model, he wanted to go ahead. So it says here he subscribed. I'm like, he subscribed. This is not like subscribing on YouTube, right? But he agreed with the plum pudding model. So he tried to confirm Thomson's model. So it's culture, it's appropriate in science. If you read about somebody's work and you want to confirm the work, you can go ahead and repeat the experiment in your own lab. And if you're able to get the same results, then you can kind of put it out there. Hey, I did his work and it's true. So you're actually kind of affirming the original scientist. So that's what Rutherford set out to do. His goal, remember, was to confirm J.J. Thomson's work, because J.J. Thomson is kind of like his mentor, right? So he goes out there and his plan is to prove that this is the correct model. The plum pudding model is the right one. Well, he does his own experiment. This is the famous gold leaf foil experiment. In his experiment, he actually chose gold, and this is called the gold leaf foil or gold foil, which is essentially like aluminum foil, but it's very, very thin. And then, of course, the element is not aluminum, this time it's gold. It's very thin. So scientists perceive that if you look at the thickness of that foil, it's about 3 to 4 layers of atoms, right? So that's as thin as they could get it at that point. They're trying to study the behavior of atoms. And so his idea was he was going to pass some particles through these atoms. And depending on how the particles that were passing through behaved, it was either going to prove, well, the goal was to prove it. It was going to prove that J.J. Thomson was right. Then life happened, right? Now, the particles he was passing through came from another element called lead. And lead was releasing, so the lead put in here, which is a source of particles, was releasing these alpha particles. And these alpha particles are essentially positively charged. So that's a short form of positively. Let me write the word out and I'll be lazy. Positively charged particles. Okay, so here's the hypothesis or the idea. The goal was most of these particles will pass through the atom and everything will be okay, right? And so right here we see what he expected, that most of the alpha particles that are positive will just pass through the atom and they will be undeflected. And when they come out, it will prove that JJ was correct. Then life happened. And when things work out in the lab to where they don't match what your predictions are, you don't want to jump and say, well, I'm wrong. You want to explain what you think is actually happening. Well, most of the particles did pass through like he perceived or like he expected. But then a few of the particles that were passing towards the center of the atoms were actually deflected. Some of them actually looked like they bounced into something very hard and also positive, and they were forced back with a great force. Okay? So then he's like, oh, there is something in the core of the atom. within the atom, right there in the center, because it kept happening over and over, and then you repeat the experiment to prove it, right? When the alpha particle hit that core, it deflected. In some cases, it almost kind of appeared like it was going to go back to the source, right? So it hit something hard and it came back. And this happened over and over again. So now he has to explain. So his conclusions, based on some of the particles being deflected, some even bouncing back with a great force, is matter may not be as uniform as it appears. So you see, you don't write your conclusion in such a way to say, hey, JJ Thomson is wrong. You're keeping this objective, right? Matter must not be as uniform as it appears. It must contain a large region of empty space, the part here where the alpha particles pass through without being deflected, dotted with a small central region of very dense matter. He's kind of keeping it generic because things haven't been proven yet. So in the end, Rutherford did more experiments, and then after he did more experiments, now he came up with his own atomic model. Man, I can't imagine that time. I like to imagine drama, but as he was writing this, his heart is beating fast. He's thinking, what do I tell JJ? My experiments just showed that JJ is wrong. And JJ is my mentor. Imagine you're like walking into his office, knocking on the door. Professor Thompson, can I talk to you about my experimental results? Oh, that must have been a tense conversation. Anyway, he comes up with his own nuclear model because you have to be committed to science, not to people, right? So his model showed something different. So he has to publish this. His model is called the nuclear atomic model because remember, he just discovered there's something that we will later call the nucleus. At first, he called it very dense matter, very generic, right? Later on, it's called the nucleus. So the nuclear theory of the atom has three basic parts, like it says here. First thing, remember, this is based on his results. Most of the atom's mass and all of its positive charge is contained in a small core called the nucleus. Most of the actual mass of the atom and the positive charge that he observed was fixed in the nucleus, right? Most of the volume of the atom, as we know, is mostly empty space. Yeah, you have electrons, right, throughout which very, very tiny negatively charged electrons are dispersed. So remember, he's trying to describe this picture here in words. The nucleus is positively charged. This is our nucleus. Nucleus. It's positively charged and it's very dense. And he's saying this is essentially where your mass of the atom is. Mass of atom. Then he's saying the electrons are spread throughout the whole volume of the atom. If the atom is big because there's a bunch of electrons just spread out there. Then he's saying, even though we know the electrons are there, they're so tiny. So it's almost like they're not really even there. But we know they're there. That's the only way to get the neutral atom, right? Not only that, didn't we just say J.J. Thomson proved they were there? Yeah. We're told there are as many negatively charged electrons outside the nucleus as there are positively charged particles, protons, within the nucleus. So the atom is electrically neutral. So some of the stuff he's saying, he's kind of building up on JJ's work, but he's making it more crisp now because he actually has names for these. So you can see here, he mentions the protons. Ooh, protons, if I can spell. He mentions the protons being positively charged. And then he mentions the nucleus. So Rutherford is giving credit for both those, the subatomic particle and the nucleus. Okay, so Rutherford, nucleus, and proton. Okay, so life went on. Rutherford's model was highly successful. Once again, I don't know why they don't publish the drama. I want to know what happened between him and JJ. Have I gone to look for it? No, I haven't gone to find the information. So I just make up my own stories. But could not explain why the mass of the atom was greater than the sum of protons and the electrons. Now Rutherford said before, mass of atom is essentially mass of nucleus. Okay? So they're saying here, yeah, but he also said the nucleus was positive. So let's do some reasoning here. He's saying mass of nucleus is equal to mass, essentially, that's what he was saying, Rutherford, mass of atom. But at that point, Rutherford thought that the nucleus only had protons. So he unintentionally was communicating that mass of proton equal mass of atom. Well, scientists said, okay, fine. So if you take the mass of proton, add the mass of electrons, even though we know electrons act like they have no mass, right? These are technically almost massless. And you add these two, you still don't get, they're not equal to the mass of the atom. So there's something missing. They're not equal to the mass of the atom. After further experiments, later, a scientist who is actually Rutherford's student called James Chadwick, he did a lot of work previously and demonstrated there was another subatomic particle that was not very popular or even scientists aware of it, that was neutral, and that was the one that was producing the remaining mass. So long story short, Chadwick, a student of Rutherford, comes up with a neutron. And he says the mass of the neutron is similar to the mass of the proton. Neutrons have no electrical charge. So what's the summary of what we've learned so far? Let me summarize this. Summary. Atoms are they are divisible. Divisible. So I'm just going to spell it out. Dalton was wrong to conclude they were indivisible. What is our proof? Atoms have subatomic particles. We just learned them, right? They're electrons, complements of J.J. Thomson. We have protons from his student Rutherford. We have neutrons from his student Chadwick. So thanks to these three scientists, now they're telling Dalton he was wrong. Once again, it's not personal. That's why the textbook are not written this way. I'm just the one who's trying to create drama here. Okay? That Dalton was wrong. They don't write it that way, but it's implied. And their questions, sometimes you see questions where they ask you things like that, right? In what ways was his conclusion disproven or something like that? Okay? So from here, then we can confidently continue and say that all atoms are composed of subatomic particles. Now, if you go into physics, they go into even deeper stuff. Chemists, this level here is comfortable for us. Higher level chemistry starts to look a lot more like physics, okay? But at this level here, Gen Chem level, protons, electrons, and neutrons are the three subatomic particles in the atom. So essentially, if you add all these three, you get the mass of the atom, right? Now, I kind of told you guys earlier that the mass of the electron is considered not significant, right? So when you look over here, the protons and neutrons have nearly identical masses. Let's look at the numbers. We have protons, neutrons. These are both in the nucleus, right? Look at the atomic mass. No, sorry, subatomic mass. Look at the subatomic mass here and here. These are nearly identical. They're very close, right? Except for these last three. Okay. When you compare that with the electron, it's all about comparison. Look at the superscript right here. This number, negative 27, negative 27, negative 31. When you add these three and you round the numbers up, this number here, whatever this number contributed to the sum, ends up rounding off. So by itself, the electrons are not massless. But when you're comparing them with this, so compared to protons and neutrons, electrons are massless. Okay? Compared to those. So essentially, when people think about the mass of the atom, they say the mass of the atom, they don't even bother with the electron, is the mass of protons plus the mass of neutrons. I was teaching this in the non-majors class one time, and somebody was very upset, and they were saying, what? It's like you're saying that the contribution of the one person or the least person is not significant. And I'm like, man, that was so deep. I didn't know you could take this that deep. In the context of rounding up numbers, which is not personal here, when you round up the contribution, so to kind of make it easier for us to see, I like this table here. You see how they wrote the masses of the subatomic particles right here. This here. They made sure that it was written to the same power negative 27. When you add these three numbers, these last three digits are affected. But when you're doing calculations, most of the time you round those numbers off. So it would be like this number here was never added. That's what they mean when you're comparing these three numbers. The addition or the contribution of the electron when it comes to the mass is not significant. Okay? But I told the student to make her feel better. Most of everything else we could talk about in chemistry is about the electron and what the electron does. Okay. So once again, remember the charge we use here. If you've had high school chemistry, +1 for proton, -1. It can be written like this or this. Either one is fine. Okay, so we got proton, we got neutron, we got electron right here. These charges that we tend to use, these are technically relative charges. If you need the actual charge, come over here to the slide. Okay, let me see how I'm doing. Okay, so I want to go over the atomic symbol and then I'll let you guys go. Okay. So now, what do the subatomic particles tell us about the elements? We're told that the elements are defined by their number of protons. When they say defined by, I'll just say identified, okay? Identified. So if you're trying to figure out what elements you're dealing with, down the road you see, we identify. There are a lot of identity numbers in chemistry. Remember earlier we said mass ratio was an identity number? Mass ratio. Now we're seeing, yeah, that one, identified compounds. Now we're seeing that protons identify elements in the periodic table or wherever, okay? So the characteristic, if you're wondering why are these numbers used for identification, kind of like your social, right? Your social should not change. Your social is yours. It's used to identify you. So if they use the social security number to identify you, that means that number is the same for you all the time, right? So these two numbers here are used to identify the element because they're constant. Okay? They're constant all the time. That means if it changes, it only changes because you're dealing with a different element. If it's different, like if the social is a different number, it's a different person. So it's constant all the time. Okay, so yeah, this is for identification. Okay, so the most important number, the protons, that is tied to the identity of an atom is the number of protons. So it's very important for us to look at the number of protons and use that to identify what element am I dealing with. So it's kind of like the many different ID numbers, right? Your ID number in college, all those numbers. The number of proton, once again, defines the element. When you're looking at atomic symbol, we're told here the number of protons in the in the nucleus of the atom is given by this symbol Z. So Z usually goes with atomic number, and this is also, so Z equal atomic number and equal proton number. Okay? And so we're told here, elements are arranged in the periodic table by their atomic number. Later on, we'll learn that the old periodic table, before the newer one that we're using, the modern one is the one that we're using. The elements were arranged according to the atomic mass. But we're being told the one that we use right now, the modern kind, is arranged according to the atomic number. Okay? The elements are represented in the periodic table by symbols and atomic number. I mean, there's more to it than that, but they're kind of giving you a simplified version. Depending on where you find your periodic table, the periodic table will be designed for different purposes, right? I've seen some that have configuration here, they have boiling point, melting point, whatever, density, so many different information. So the basic we have, though, for the ones I've seen, most of the time we'll have the chemical symbol of the element. Some have the name. There's some that don't have the name. Different periodic tables are designed for different purposes, right? So sometimes if you want one that has a specific purpose, like say the name, you want to actually, if you're Googling to find it online, Google periodic table showing name. Okay, that will help you to get more of what you're looking for. So this one here shows you the element, the symbol, right? The actual name with the correct spelling, and then finally the atomic number. As I said, you have different kinds of periodic table with different information. So what I'm going to do here is, as we go through here, actually, since time is up, I'll just say start here. So on Wednesday, oh, we're not doing that bad. On Wednesday, we'll start here. Once again, as you're working on your homework, even though it took me a while to figure out exactly what they wanted and the format. Sometimes, once again, with the homework, the programmer who programs the answers programs it in a very specific way. If you cannot get it exactly that way, you won't get the answer right. If you're having that kind of problem, email me, come to the lesson, and then we'll figure it out, because at that point it's kind of a formatting issue. That way you don't lose those points. Okay? So when we meet on Wednesday, we'll continue this chapter. It shows here that we have about 24 slides to be done. So we'll finish this, and if we're done early enough, we'll start with the next section. Okay? If you guys have questions, please bring it to the lesson, and then we'll go over that. Other than that, I'll stop here because it'll take me a while to go over into the isotope. So I'd rather just do this on Wednesday. Do you have any questions? Does anybody have any questions? Okay. Okay, you're welcome. So y'all have a nice day. That's okay. I will see you guys on Wednesday, right? And between now and then, once again, if you have any questions, just send me an email, and then I'll get back to you as soon as I can. Okay. Thank you. Bye. Let me go ahead and log off here.